I'm doing a master's degree in engineering, and in 6 months I'm supposed to submit in my thesis. I figured I'd share the first month of my work because I think it should be interesting, especially since I haven't started yet. So this is kind of the robot I want to build. It's an agile biped robot. It has 2 legs and wheels instead of feet on which it can drive around. One of the main parts of any robot are its actuators. I had used servo motors for all of my previous builds, but this time I was gonna challenge myself and use robotic actuators instead. So I did some digging around and I managed to find these actuators. 22 Newton meters of torque, 320 RPM. I have never used an actuator before, so everything I'm gonna do with them is gonna be my first time. I also noticed that these actuators would cost more than half of my net worth, and they came with 2 different drivers, GDS68 and GDZ468. I didn't know which driver is better, so I ended up ordering both of them, and after 2 weeks they arrived. So the goal for today is going to be getting these actuators to spin. The first thing I did is I scanned this QR code and I downloaded the official files, and they look like this. So the documentation is in Chinese. Yeah, this is gonna be hard. A few PDF translators later, I was able to read the documentation and it led me to download these 2 files. This file is for installing the driver and this file is for controlling the motor. I connected the actuator to my laptop with a USB-C cable and I powered it with 24 volts from a 6S LiPo battery. Then I filled in all of the motor parameters for the driver, which I just got from the website I bought the motors from. All that was left to do then was to click the calibration button, which I was pretty nervous about as I didn't know what the calibration does. It was completely fine though, as the motor just started spinning to one side really slowly, then it stopped and spun the other way. The motor then beeped, indicating the calibration was successful, and I was able to start experimenting with position, velocity and torque control. So this is position control, speed control, 40 RPM, 80 RPM, 120 RPM. I was really happy with the actuator's performance and I immediately wanted to buy 6 more of them, which I needed for the robot. Before committing to the purchase, however, I decided to check 2 more things, the first of which being the motor's torque. So I'm going to go into the torque control mode and I'm gonna command the motor to exert some torque and I'm gonna measure it with this weight. As you can probably see, I'm kind of scared. Fuck. Fuck. After some failed attempts, I changed the input mode to torque ramp, that way it gradually increases the torque instead of just smashing into the weight. So the torque is just gonna be the weight times g. This is gonna give us the gravitational force, and if we multiply it by the length, it's gonna give us the torque. The highest weight the weight was able to measure was 2.3 kilograms, 10.7 Newton meters. After measuring the torque, I checked the data sheet and realized that the stall torque of 22 Newton meters is about twice as much as what I measured, and I just figured it's because I haven't inputted the correct motor parameters. This was also the first time I saw the motor parameters listed separately for each driver, and I immediately realized the second driver has much lower power and it's basically a waste of money. Until now, I have been controlling the actuators through the Motor Wizard app on my laptop, but for the actual robot, I'm gonna need to control them with a microcontroller. There's 0 chance of this working, but we'll see. What a fucking surprise. After realizing that the circuit and code entirely made by ChatGPT is just not gonna cut it, I had to figure it out myself. I got this actuator and I want to control it with a microcontroller. The actuator uses CAN bus for communication, so I obviously need an MCU that is capable of it. I chose Thesis 4.1, which is basically an Arduino on steroids. I can't just connect the MCU to the actuator directly, I need a CAN bus transceiver. This transceiver translates the logic signal from the Thesis to the CAN bus differential signal used by the actuator. The output of this transceiver are 2 lines, CAN high and CAN low. These lines are used to communicate with the actuator. At each end of the main CAN bus line, you also need to add a termination resistor. These are used for impedance matching, so when you send a signal, it's not gonna bounce around, but it's gonna get dissipated through the resistors. Now we're getting into the main advantage of CAN bus. CAN stands for Control Area Network, and this means you can add as many actuators as you want by just adding 2 wires. One thing to note is that these lines should be really short. Ideally, you would have these actuators daisy-chained like this. In my experience, however, this communication is really robust. For example, I haven't used this resistor and I used 220 ohm resistor at the end because I can fucking read, and it still worked perfectly fine. In the end, I managed to get the motor to turn and I ended up ordering 6 more actuators. This actuator has a port for USB-C, so you can plug it into your laptop, and then you have CAN high and CAN low pins. You have this connector called XT30 2+2 because it has 2 pins for power and 2 pins for CAN bus. I also got this special wire. It's basically 2 wires twisted together so that when one wire picks up noise, the second wire picks it up too, and then when you measure the signal across them, the noise gets subtracted. So in my circuit, I'm gonna connect this cable to each actuator, then I'm gonna have this main CAN bus line and connect these actuators parallel to it. Once I knew what the circuit is gonna look like, I went ahead and started designing a custom PCB. This would allow me to connect all the components together by plugging them into a single circuit board instead of soldering a bunch of wires together and having everything messy. To design the PCB, I opened up KiCad and went straight into the schematic editor. This is where you drag and drop your components and wire them together. For example, I have the Thesis MCU, I have the CAN bus transceiver, and I want to be able to plug these components into the PCB. So in the schematic I found a symbol for Thesis 4.1 and I found a symbol for a generic pin header in which I can plug the CAN bus transceiver into. All I needed to do then was to wire them together, and instead of using the wire tool, I used mostly labels to make it more organized. After placing symbols for all of the components and wiring them together, I was left with this schematic. At the center of it there's the Thesis 4.1 MCU. I got 2 6S LiPo batteries wired in series through a screw terminal block. That way I get 48 volts, which then goes through a switch. When the switch is turned on, this then powers 6 screw terminal blocks in which you can plug in the motors. There is also a pin header in which you can plug the CAN bus transceiver into, and that connects it to the Thesis 4.1. Lastly, I added a power supply which takes in the 24 volts from the lower LiPo battery and steps it down to 5 volts to power the Thesis microcontroller. I also added these redundant power pins in case I need to power up some sensors. So this is the schematic, but to tell KiCad which exact components I was gonna use, I needed to assign the footprints. For the pin headers, I measured that the pitch is 2.54 mm, which is standard for Arduino, and since the pins on the CAN bus transceiver were male, I used a 1x4 vertical pin socket. For the Thesis 4.1, I had to download the footprint of the internet. After assigning footprints for each of the components, I could finally go into PCB editor and start making the actual traces. Firstly, I went into the edge cuts layer. This is where you define the shape of the PCB board. I made sure that my PCB is 100 by 100 mm because at this size it cost only $5 with PCBWay. After I had placed all the components onto the PCB, I went into the front copper layer and started making the traces. Since I had defined all the connections in the schematic previously, this forced me to not make any mistakes. After a few hours of making the traces, I was left with this nice PCB. So this PCB looks pretty complicated, but that's just because there's many components. So this is the front layer, this is the back layer. I mainly try to use the front layer for the 48 volt line to get power to the motors. I actually used a filled zone, that way the current doesn't flow only through these traces, but through the whole surface of the PCB. I did this with the back layer as well, where I attached it to ground. This was done mainly because the current flowing through this PCB is gonna be really high and I wanted to minimize the resistance. After making the traces, I also made sure to describe each component onto the PCB. That way when I'm connecting the motors, I know where to plug the 48 volt cable and the ground. After the PCB was finished, I was able to check it in the 3D viewer and it was time to export it. I did this by clicking plot, selecting a folder in which I want to export the files into, and clicking plot again. After this, I also generated the drill files which are necessary for making the holes. Just like that, the PCB was finished and I sent it to PCBWay for manufacturing. I selected the size of my PCB, quantity, and the color. The total cost of the PCB was $5, and after uploading the Gerbil file, I was able to track the manufacturing process in real time. If you're also interested in getting some PCBs, definitely check out PCBWay. They have a Christmas sale right now where you can get stuff up to 50% off. They got coupons and special offers not only for PCBs but also manufacturing services like 3D printing, CNC machining and injection molding. They also have this PCBWay store where you can get things like multimeters and microcontrollers. So if you're gonna be building some projects this winter, definitely check them out and take advantage of this sale. Since I got the PCBs, I could start soldering up the components. I recently bought a new soldering station, I think it's called Hako, and it's industrial grade. It was kind of expensive, but I think it was worth it because it ended up saving me about 2 hours on this PCB. As I soldered the THT components, I also needed to solder a buck converter, which is SMD. And I didn't have a new one, so I just used some old shitty one from a different PCB. This actually ended up fucking me over quite a bit, which I had no idea at this point. I have finished soldering this PCB. I really like the look, especially the purple color. I just noticed that I melted these few pins. In case I fucked up wiring 2 batteries in series after taking 6 years worth of engineering classes, I'm going to check the circuit with a multimeter. After checking the whole circuit and making sure it's completely fine, I decided to plug in the 2 LiPo batteries and turn it on. I was pretty scared at this point because I have never used a 6S LiPo battery and now I was gonna use 2 of them in series. It ended up being completely fine though, and after measuring 46 volts on the actuator terminals, I was able to connect the actuator and started tuning the PID gains. The actuator can already turn decently, but to make it perform better you need to tune the PID gains, especially after changing the load. The structure of the motor controller is cascade, so you have current loop on the inside, then you have velocity loop, and on the outside you have a position loop. This means that if you want to send a position command to the motor, it gets translated to velocity command, which gets translated to current command, and even then this goes to a low-level FOC controller, which makes sure that the motor uses the current efficiently to generate torque. The generated torque then makes the motor accelerate, and over time you get velocity and the desired position. But for now you just need to know that each of the controllers, the position, velocity and current controller, each have 3 parameters, P, I and D, although the loops don't use all of them. And these parameters need to be tuned correctly in order for the motor to turn nicely. Otherwise you can get stuff like overshoot, low response time and undesired behavior. It probably sounds insane, but the most used technique for tuning PID controllers is just guess and check. And the manual for this actuator actually has an algorithm for tuning it. So firstly I'm gonna turn on the motor. And now I can connect and disconnect the actuator to my laptop. So I got the speed loop, KP, KI, then I got the position loop. I'm gonna do this according to the manual. So I'm gonna start with these parameters and I'm also gonna set velocity integrator gain to 0. I'm gonna put that to 0, 0.2, 0.42. Firstly, they want me to tune the velocity gain. I have to increase this gain until the motor turns horribly. It turns well, so I'm gonna increase the gain. Right, so we found the limit, it's about 1, and now they want me to lower it by 50%. So with position gain, they want you to find the critical position and then just slightly lower it, pretty straightforward. It kicks so hard. So you can see this one peak, that's the overshoot. I'm gonna lower the gain. Now the last thing we need to tune is velocity integrator gain. I'm going to use this example they gave, maybe 10 times the velocity gain. Let's try that. I got the actuator tuned pretty well, and the next step was to control it with the teensy microcontroller. I had actually done this before when I was first testing the motor. However, at that time I only had velocity control and the code was entirely written by ChatGPT. I thought I was gonna get away with using ChatGPT for writing the position and torque control functions, however this was not the case. The task ended up being much more challenging than I expected. I have been coding for like 5 hours trying to get the control commands to work, and unfortunately it doesn't work at all. If I try sending a position command, this is what happens. It just stays at 0 all the time and it doesn't move at all. What's cool about this is you can feel the torque feedback, so it's pretty cool to actually feel the force. Now I'm gonna show you velocity command, which is the only one I managed to get working. Kind of tired of coding right now, so I think I'm going to go ahead and build the test stand. I haven't mentioned this yet, but ever since I ordered the 6 actuators, I have been working on the robot's leg in the background. So this is the Fusion 360 assembly. The leg uses 3 motors, 2 are for moving the leg and the third one rotates the wheel. The wheel is going to be rotated through a double belt drive. This motor is going to rotate the first belt drive, which is going to rotate the shaft on this calf motor. The motion is going to be translated through a second belt drive to the robot's wheel. It's super complicated, but I wanted to build it this way to minimize the weight of the wheel. That way the robot can jump higher. After I finished designing this leg, I also went ahead and designed a test stand for it. This test stand is going to be made out of 2020 aluminum extrusions. It's got this rail which the leg is attached to. That way I can test the movement of the leg, and I can also load up the leg with some weight. This test stand is very long, and that's because once I build the whole robot, I plan on taking this rail and mounting it onto this extrusion. That way the robot can move forwards and backwards while holding its balance, and if the robot fails for some reason, it's gonna get caught up by the cart and not destroy itself. The test stand is made out of a bunch of extrusions bolted together with M6 bolts. So the first thing I did after clamping the extrusion to my table is I started drilling the hole. I found this chart online which told me that to make M6 threads I needed a hole of 5.5 millimeters, and I used a 3D printed guide to make sure the hole is straight. After I got to the tapping, I applied a generous amount of WD-40, and I used this technique I learned from YouTube, in which you turn the tap once and then turn it halfway back to break the chip. Although I very quickly switched to my own technique, where I just turned the tap until it was hard to turn and then I turned it halfway back. I always heard these rumors of people breaking taps, especially from my high school classmates, but I've never actually broken a tap, and this time was no different. One thing that I hate about working with metal is the mess it makes. The chips are just the nastiest things to get rid of. Even if you use a cloth, it's really hard to wipe them off. And since I'm doing this in my apartment, having metal chips around is not ideal. Having finished making all the threads, I also needed to drill a few clearance holes, so I would have access to the bolts and be able to actually tighten them. And at this point my drill started burning up. I only needed like 2 more holes, so I sacrificed my lungs and finished the job. As I was assembling the test stand, it was kind of annoying because all the nuts I wanted to use needed to be put inside the extrusions before I bolted everything together, otherwise you have no way of getting them inside. Attaching the rail was also pretty annoying because I needed to attach 2 end stops to it, which I printed from TPU, and I also needed to attach the rail itself to the extrusion. I of course fucked this up like 2 times, so I had to disassemble part of the test stand and then reassemble it again. As I was getting close to finishing the assembly, I realized just how big the test stand is and the fact that I probably should have made it smaller. It takes up most of my table and I wasn't even sure how I was gonna film things. It also vibrated quite a lot. At this point I had also started using my brain instead of ChatGPT and figured out how the CAN bus communication protocol works. I just want to capture this moment because I have spent the last 6 hours going through the code trying to get this motor to work in position mode, and I finally did it. I'm going to place this bolt right here and the motor should spin 180 degrees. Very nice. So why did this take me 6 hours? Well, there were like 16 errors in the code and I fixed all of them. There was still one issue remaining, and that was this ID. It is supposed to be 0x, that's like hexadecimal number, 00B, and I had it set to 0B0. So, lesson learned, ChatGPT is real bad with facts. I just gave it like the manual and I wanted it to take the numbers and copy them into code, and it fucked it up. It's my stupidity that I didn't check it. At least I learned something about the CAN bus communication, like how to send and receive messages and things like that. So it wasn't a waste of time, but it was still frustrating. Now I'm gonna show you my understanding of the CAN bus protocol. This was the most important thing about this whole project, because once I understood it, I was able to code every single function for the actuator. This is the format of the CAN bus protocol. Firstly, you send node ID. This way you're telling the protocol which actuator you want to communicate with. Then you send command ID, so each command has its own ID and you need to send that. Finally, you send 8 bytes of data. This data is the input to the command you are sending. Since each function is gonna have this same format, I wrote a function for it. I used a library called FlexScan T4, I think, and it's just the format encoded in this function. So motor ID, command ID, 8 bytes of data, and this function just uses the CAN bus protocol to send CAN messages. Once I had this function, I could start writing functions for actually controlling the actuator. This is the simplest example, velocity control. This is what even ChatGPT was able to write, although I had to write it myself in the end to make it not be shit. So for velocity control, you need to know the motor ID, velocity in revolutions per second, and then you actually set feed-forward torque in Newton meters. You might be wondering why you need to set torque when you want to set velocity, and I'm gonna get into this later. Firstly, the function applies the actuator reduction. The actuator has an encoder on the motor, not on the output shaft. Between the output shaft and the motor, there is a gear reduction of 8:1. So to set the revolutions of the output shaft, you need to multiply it by the reduction ratio, which is 8:1. And this part is crucial to understanding the CAN bus protocol. Data needs to be 8 bytes, and you can just find this in the documentation. You need to send two values: 32-bit float velocity and 32-bit float torque. And that's what's happening in the code. 32 bits for velocity, that's 4 bytes, and then 32 bits for torque. That way you get 8 bytes and send them via the sendCAN function. This is pretty simple, but for the position function, this gets a bit confusing. For setting the position, you again set motor ID, position in revolutions, feed-forward velocity, and feed-forward torque. Since you have more inputs and you still need to fit into the 8-byte data, you actually need to encode it in a different way. The input position is a 32-bit float. For velocity and torque, you actually used a 16-bit integers. So for 32-bit float position, you get 4 bytes of data, and then you send two 16-bit unsigned integers to fit into the 8 bytes. The default units are also different, and this is why I multiply the torque and velocity inputs by a factor of 1000. At first I was a bit confused, so this is set position function, but you need to input not only position, but velocity and torque as well. At first I thought it meant, hey, motor, move to this position, but do not exceed this torque and do not exceed this velocity. But that's not what it means at all. So this is the block diagram of the microcontroller. If you want to send a position command, it gets translated to velocity and then to current. That's because the structure is cascade. The feed forward factors actually just get added up to the velocity command. So this way you are anticipating the movement. For example, if you expect the actuator to move really quickly to reach that position, you can set a high feed-forward velocity, and that way the actuator is going to respond much more quickly. Then you're going to use this example. So if the input position is this step function, if you do not use a feed-forward velocity, the regulators need a bit of time before they kick in, so you're probably going to get this green line which lags behind. But if you use the feed-forward velocity, the regulators are going to use a high velocity at the start. This way you get quicker response and it doesn't lag behind that much. So these are the basics of the CAN bus protocol, and with them I was able to write every single function for controlling the motor. So I'm using a specific actuator with a specific driver, but I'm pretty sure it's gonna work on most actuators, although don't quote me on that. And this is why. So as I was reading the original documentation for my actuator, I noticed it keeps referring to O-Drive. I had a suspicion that it's basically a Chinese copy of the O-Drive Microcontroller, because for all of the code I used this official O-Drive documentation and it ended up working on my actuator. So I think even if my actuators get sold out in a year or two, if you get any other actuator that also uses the CAN bus protocol, it's probably gonna be the exact same. I'm gonna put the code up on my Patreon as well as all the other files for this project, so if you wanna support me, you can check it out. I was pretty happy with my progress as I finished programming these actuators, but I was just about to find out some bad news. So the encoder in this motor is absolute. That means that the motor is gonna remember its absolute position even when you turn it off and on. The bad news is that the absolute encoder is on the motor before the reduction. So right now the position is set to be 0, and if I turn it on, it moved to the 0 position. If I move it slightly away and turn it on again, it moves back to the 0 position. And this is exactly what you want. The problem is when I turn this more than about 16th of the turn, this is the new 0 position. It's offset. And that's because the encoder doesn't read the rotation of the output shaft, but the rotation of the motor. And between the output shaft and the motor, there is a gearbox which has a reduction of 8:1. So when I turn the output shaft by a quarter, the motor inside this actuator actually turns 2 times. And that's why it loses the 0 position. And this fucking sucks. It means I'm gonna have to either use limit switches or like get the 0 position out of the current. It is especially sad since I could have bought the second encoder for $40 more. But you know what? I was able to solve the position problem, so I'm gonna solve this as well. Despite my spirits being crushed by the lack of secondary encoders, I started building up the lag. I labeled each actuator based on its ID. Then I plugged it into my laptop, and in the Motor Wizard app I pasted in the electrical parameters and also the PID gains which I have obtained earlier. I also noticed that some of the main parts were printed from the old shitty PLA when I was doing the testing, so I reprinted them from PLA Pro. I have been using this filament for some time now, and since I like it so much, Instalogic sent me 30 kilograms of it. So 1 kilogram of white PLA, black, blue, and then about 32 kilograms more. I almost broke my back trying to get this upstairs. They also sent me a few rolls of TPU, which I used for the robot's wheel because it's squishy. Instalogic offers free shipping, and they have a Christmas sale, which means that if you buy 4 kilograms of filament, it's gonna cost you only about $50 with free shipping, and you also support me because I get commissions. You can check out the description and use my referral link. This is where I started having second doubts. The lag was insanely big, and although that was the intention and I planned on cutting the carbon fiber tubes shorter after initial testing, I couldn't even do that because the lag didn't fit onto the test stand. It was also becoming obvious that I do not have enough time for this, so I reduced the complexity as much as possible, went into CAD and remodeled the whole robot. Since I had modeled the robot with parameters, this took only a few hours, and with the 3D printing taking only a few hours as well, I could start assembling the new design pretty quickly. So I finished assembling the leg, I did the wiring, and I started getting pretty excited, because after a month of work, I was gonna move the leg for the first time. The first thing I'm going to try to do is to get this wheel spinning. Alright, I changed every single ID of the motor to 3, then I set the mode to velocity, and then I just set the velocity to 1 revolution per second. So I'm just gonna upload this code and we're gonna see if it works. Oh, that's awful. Yeah, I have no idea what happened. Like, it just blew up. I flipped the switch and the electronics immediately burned up. This was really confusing to me because I had tested the circuit before and it worked fine, but now there was a short circuit between 5 and 24 volts and the buck converter was dead. This also caused more issues downstream. The shorted buck converter fried my TNC with 24 volts, and since the CAN bus transceiver was powered by it, it got fried as well. I was also worried that the 24 volts got onto the CAN bus line and fried the CAN bus transceivers on the actuators. To find out if this was the case, I would have to test the actuators. It is like a week later, I got new MCU. Since I desoldered the buck converter, there's no short circuit on the PCB, and I decided I'm going to power the microcontroller with USB. Fortunately, the actuators weren't damaged and I was pretty happy about that. I was already imagining a YouTube thumbnail, my most expensive mistake, and then the thumbnail would be just 3 motors that are burning. It would be pretty funny, but I'm glad I don't have to do that. Another issue I needed to solve was the second encoder. Since the actuators didn't have an encoder on the output shaft, I wasn't able to tell the absolute position of each motor. At first I wanted to solve this by just straightening the leg out, that way physically each angle of the actuator would be 0, and then whichever angle I read in the code, I would just set that to be 0. The leg was too big to straighten out though, so what I ended up doing is having it be at a set height. I measured angles of each link and calculated the physical angle of each actuator. This way I knew the actual angles of the actuators and I synchronized them with the perceived angles from the code. This solution wasn't ideal, but I needed to move forward and finally make the leg jump. Since I wanted the foot to move in a straight line, I needed an inverse kinematics function in which I could input the XY position of the foot and get out the necessary motor angles to achieve it. I did this by stealing my own code from the latest video. Since I had programmed this function before, I could just upload it onto my new robot and knew it was gonna work. So right now it's obtaining 0 offsets. Fuck. That was about 20 times worse than I expected. So usually inverse kinematics for these 2 linkage manipulators has 2 solutions. If you want XY point, you can either reach it like this or like this. So it has 2 solutions and I was pretty sure I solved it for the correct configuration, but apparently not. Since the leg was moving up, I knew the IK worked and I just needed to flip the solution by inverting the angles. Peach. At this point I decided to limit the power to the actuators. There's this function I created called set limits. It sets the velocity limit and the current limit. Since current is proportional to torque, this limits the output torque of the actuators. So if I turn this on, the commanded velocity is 1 revolution per second. And you can see it's slower. That's because I set the velocity limit to 0.2 revolutions per second. I'm also limiting the current so I can grab the wheel with my hand and overpower the actuator. The leg was not much safer, but a different issue arrived. Okay, things are getting scary. I originally wanted to use filter position mode. That way the leg moves smoothly up and down. The filter is too slow and I don't know how to change that. So I'm gonna use pass-through mode, which means that the movement is gonna be jerky and the leg is gonna be moving at its limits. So I'm gonna start with the limits being kind of low and then increase them to the maximum so I can make this leg jump. The first test went okay, but the leg was kind of weak. The current limit is set to 6 amps and the maximum is 50. Let's triple it. Jump test number 2, current limit 20 amps. Okay, that was pretty cool and maybe a bit scary. Jump test number 4, current limit is 40 amps. This was my first time using these actuators and I managed to make them work, which I'm super happy about because I want to graduate this year. If you like this content and you want to support me, you can do that on Patreon and you will get the code for these actuators, which I will continuously upgrade as I work on my thesis. So thank you guys for watching and I'll see you soon.